Now that we've familiarized ourselves with the concept of moments, we're going to look at this idea of equivalent forces. And these are really similar to our resultant forces, except they're acting on a body. So instead of acting on a single point, as we've looked at with resultant forces in the past, these are now acting on a body. And you could have multiple forces acting on some body in many different points, many different ways, and even moments acting on a body, acting a rotation on the side of this body, right? So we could have moments and forces acting on a body, and we can turn that into an equivalent force. And just how we found resultant forces, by taking the sum of the forces in the x direction, that gives us our x component of our resultant force, the sum of forces in the y direction, giving us the y component of our resultant force. And now we'll also introduce this moment, this resultant moment, from all the ones we've been talking about, which is just the sum of all of the moments about a point, plus the sum of any moments that just exist in the wild, just exists like this one acting on this body, right? So we would take a moment about a point for each of the forces, and that would go in our first term, and our second term here would just be adding in any moments that are actually acting on the body itself. And so we'll usually see these in 3 different types of contexts. Usually concurrent forces, so forces that act on the same point, right? Their line of action goes through the same point. So if I have a force here and a force here, their line of action intersects here. So that's one, this concurrent forces. We also see it a lot with coplanar ones, so ones that are all within the same plane, like the XY plane. See it a lot in 2D. Like this one, for example. The first one that we drew is an example of a coplanar one. F1 and F2 share the same plane. And any forces that we were to add on to this would also share the same plane, right? It's in 2D. This is in concurrent, coplanar, and then we can also see this sometimes in a 3D system where the forces are all parallel, right? So maybe I've got, one force acting down on this plate, a force coming up from this plate. Here's another force, and they're acting at different points on the XY plane, but they're all parallel to each other. They're all completely vertical, right? They're all on the z-axis, right? All parallel to the z-axis. This is a parallel force system. Oops, parallel. That's an A. Parallel, parallel force system. These are typically the situations where we'll see these, and our goal with these is to simplify the system, right? Take all of the forces that we see and make it into one single resultant force and a single resultant moment. So we'll take a look at some examples. In this example, I'm given a beam that has 3 different forces acting on it, as well as a moment acting on the end of the bar. And it asks me to replace this force system with an equivalent resultant force and a moment acting about point P. So the resultant force is going to be the sum of our forces, right? I'll take the sum of my forces in the x direction, the sum of my forces in the y direction, and I'll use that to find a resultant force. And remember, there are 3 ways that we can kind of identify this resultant force, right? We can do it with Cartesian form, right? I'll put this off to the side here. So to give direction, we can do it in Cartesian form, right? That's our IJK form. We can give a magnitude and the angle. Or we can give just directional arrows. Directional arrows. So for this one, I'm going to go ahead and do my sum of my x forces. This will be in the positive x direction this way. Right, if I take my sum of my x forces in this example, I only have one force pointing in the x direction, right? It's the x component of the 50 Newton force that's pointing off this way. So my x component is going to be 4/5 because this is a 3, 4, 5 triangle on our 50 Newtons. 4/5 is the ratio of the x component times 50 Newtons. So my x component is just 40 Newtons. And I can give a directional arrow to that. I can just say positive x direction. I can leave it like that. And then I'll do my y. My y component. Right, so my y component, I'm actually going to make the negative direction positive. And I know that sounds weird, right? But if I look at it, all of my forces in the y direction are pointing downwards. So I can just say that my down is going to be positive in this case. And I can say I have 40 plus 30, that's the first two forces listed there, plus the y component of my 50, 3/5 times 50 Newtons. And so what I end up with here is I have my Fy is 100 Newtons in the negative y direction, right? So I just note these with directional arrows. So these are each of my components, and then I can choose to put these in Cartesian form or give a magnitude and directional angle, right? So I can do the sum of the sum of the squares and square root that, and then find an angle. Or I can, let me write it in Cartesian form first. That one's the simplest, right? Our IJK form. So that would be negative 100 I hat plus 40. That's backwards, isn't it? Yes, it is. Okay, it is, our resultant force is 40 I hat minus 100, right? It's in the negative y direction, minus 40 j hat newtons. So you can write it just like this. This would be the equivalent resultant force. You could also find the magnitude and direction, right? So if I do 40 squared plus 100 squared, take the square root of that, I think I get around 107 newtons. And then I would also need to specify an angle, right? So that would be arctangent of a negative 100 over 40, and that would give me the angle. I don't have an angle written here. Let me calculate it really fast. Here's my, if I do arctangent of negative 100 over 40, I get where's my oh, it's in radians. All right, calculator in degrees, please. Okay, arctan of negative 100 over 40, and I get negative 68.2. I add 180 to that, right? Because I know it is in the positive x negative y, right? So it is negative 68.2 degrees. There we go. Took a second, but we got there. So either one of these are correct. Either one of these are correct. These components are also correct, right? With these directional arrows, these are also correct. But we typically see the resultant force as being the x and y components together. So you can list them separately like this, or you can have one of these two answers. Both are totally correct. So that's the first half. That's an equivalent resultant force. We'll talk in a little bit about where that equivalent resultant force is, because it does hit a specific point on the beam, right? It's not acting at point A. We're listening for the moment acting at point A. The equivalent resultant force does act at a specific point on the beam, right? So, maybe somewhere like here. And in a couple of problems, we'll talk about how we find that. But first, let's find our moment acting at point P. Okay, so our moment, not point P, our point A, sorry. Our moment acting at point A, if we take our moment about A. Now, I can choose whether I make clockwise or counterclockwise positive here. In this case, it's actually going to make more sense, instead of using the traditional counterclockwise as positive, I notice that all of my forces are actually going clockwise around A. So if I make mine clockwise, right, if I say that the positive direction is clockwise, then I can make all of these positive. And I can do my 30 newtons of force times the 3-meter distance plus my distance from A, 6 meters, and then the y component of this force, right? The y component being 40 times 6, not 40, 30, sorry, 30 times 6, right? That was the y component of our 50 here. So 30 times 3 plus 30 times 6 plus this moment that we have acting on the point. It's not multiplied by any distance because it's already a moment. So this was force times distance, and then plus just any moments that we have hanging about. So we have this 200 Newton meters clockwise, right? So it'll be positive since we made our clockwise positive. And we can say the moment about A, the equivalent resultant moment about A for this system, is just the sum of all of this. So this is 470 Newton meters clockwise. So those would be our two answers. We got our resultant force, that was the equivalent resultant force for the system, and the moment acting about point A. Let's look at another example. In this example, we have another beam system with a system of forces applied to it, right? So there are 4 forces applied to this beam, and we're going to simplify that to an equivalent resultant force and take the moment about point O. Point O is kind of this lumpy guy. He's way over to the left. So our resultant force, again, is just some of our forces in the x direction and the y direction. So some of our forces in the x direction is going to be the x component of our 500 Newton force here. So 3/5 times the 500 Newton force. And I'm going to say that my positive x direction is to the right, our conventional positive x direction. And then I have these 200 Newton forces. Now I'll notice that I have a plus 200 and a minus 200. They're acting opposite and they're parallel to each other. So these two forces here are actually a moment couple, right? These create a couple moment. So even though I don't have an explicit moment written like this, I'll know that I'll have a moment created from this couple moment pair separated by this distance of 1 meter, right? So I'll keep that in mind when I go to do my moment calculation. So I go and I get my sum of my forces in the x direction is 300 newtons, and that's to the right. Then I'll do the sum of my y forces, and this time I'll make up positive. We'll do a conventional up is positive for y, and I will have negative 750 plus the y component of my 500 newtons. 4/5 times 500. And this will give me that my Fy is negative 350. Negative 350 newtons. Which that's negative from the positive direction. So I could say negative 350 positive or 350 newtons in the negative direction. These are the same, right? These are equivalent. So if I were to write my resultant force for this, I'll probably just do it in Cartesian form. That would be simplest. I have 300 newtons, 300 I hat minus 350 J hat newtons. So that's my equivalent resultant force. And now I'll find my moment about point O. So my moment about point O, move this guy, whoops. I'll just get rid of this guy. I take my moment about point O, making counterclockwise positive, just because that's convention. Counterclockwise positive, my moment about point O, I will have my 750 newtons times this distance 1.25 away from O. And I'll notice that that is acting clockwise. So this is a negative 750. Negative 750 times 1.25. Then I'll go to my next force, which is this 500 newtons. Now notice that this is not acting on this line of action of the beam. I'm going to have to take both the x and y components of my force here, right? So for my y component here, it will be plus my y component we said was 400. 400 times 1.25 plus 1.25 is 2.5. Right, so that's the y component times this distance. Now I'll need the x component, which is going clockwise. So it'll be a negative 300 times the perpendicular distance here is 1. Then finally, I'll add on the moment couple, right? So the moment couple is creating a moment, and if we recall, the way we calculated that was just the force times distance. So plus 200 times 1, the distance between them. Now, I did a plus, but is it actually a plus? Is this going clockwise or counterclockwise? We'll see. Our rotation is going in this motion, so it is a positive, right? It's going counterclockwise, this moment couple. You can move it anywhere along this beam, and it's always going to be going counterclockwise because of the way the forces interact with each other. So if I add all of these together, I get my moment about O is 37.5 Newton meters clockwise, right? If I add all those together, what I actually got was a negative 37.5 Newton meters. So that would be negative 37.5 Newton meters counterclockwise, or, as I've written it here, a positive 37.5 Newton meters clockwise. Either way is totally correct. Just be sure you're specifying your direction with your moments. Be sure you're including that clockwise, counterclockwise, whether you write it as, is the abbreviation, or give the symbol, or write out clockwise, counterclockwise. Any of those are acceptable, but they have to be there if your moment is not in Cartesian form. If your moment is not in the IJK form, you're just giving the magnitude, you have to specify the direction. So earlier I mentioned that a resultant force, an equivalent force, is going to have a location on the bar, right? So when you find this, if I look at my example here, I have this straight bar and it has 3 forces acting on it. And when I find whatever this equivalent force is acting on this bar, it's actually acting on some location here, right? And we don't know exactly where that is. So we're going to find, in this example, where this resultant force intersects the member. Where does the line of action of this force intersect the member? So we'll do that first by finding what the equivalent resultant force is, and then using a moment to determine distance. Right, so let's find our resultant force first. Should be easy enough by now, right? Just summing our forces in the x direction and the y direction, and I'll keep my conventional directions positive. And I'm hoping that summing these forces feels a little bit easier, a little bit more intuitive to you now, because we've been doing this for so long that maybe you can pretty instantly see these forces that we're adding. Now, it would help if I remembered to give you the angle here, which is 30 degrees. Alright, there's a 30-degree angle there, so when I sum my forces in the x direction, I get 50 times the x component here is going to be sine 30, 50 sine 30, plus the x component of my force here is going to be 3/5, that's the ratio, 3/5 times 150. And then my third force is only in the y direction, so it has no x component. So I sum those, I get my x component of my resultant is 115 pounds. Right, 115 pounds. And I'll do the same for my y. Go with the conventional up is positive for our y direction. So I have that 200 pounds. And then my next force here, I have the minus, right? This next force is going downwards, minus 4/5 times 150 is the y component of that force. And the y component of our 50-pound force is going to be plus 50 cosine 30. So I plug all of that into my calculator, and it gives me that my y component is 123.3 pounds. So my resultant force, again, Cartesian form is just going to be easiest because I can just say 115 I hat plus 123.3 j hat pounds. And that's what my resultant force is. So really what this is saying is where on this line is this resultant force acting? And I can, instead of drawing it how I did as this single line resultant here, what I really have is I have this x component of my force, right? So somewhere along this line, I'll do this darker. Somewhere along this line, I have this x component of 115 acting, and then I have a y component of 123.3 acting upwards. And this is what we're interested in, right? We're interested in this distance from point A to where the line of action is intersecting our beam. So 115 is traveling horizontally through the entire beam, right? So if I take a moment, the line of action of the force is going through point A. So we're not going to be taking the moment of the 115 pounds. Instead, it's only going to be the y component of the force. The y component is what's intersecting the member. And this is the distance d that we're looking for, right? Let's specify where the resultant force intersects with the member. So this is what we're looking for. Where, at what distance away from A, is this force intersecting? So the way we do that is by taking the moment, right? And only the moment of the portion that's intersecting. I move this out of my way. For the second half of this, I have, if I take the moment about A, I get, for all of my forces here, I'm going to get 200, right? 200 times this 3. 200 times 3, that's the moment for my first force. Then I just need the y component of this guy, right? Because the x component is in the line of action of A. So I only need the y component here, which is minus, right? Because it's going clockwise, minus 4/5 times 150. That's the force component. And then the distance is 3 plus 3, so 6 feet. And then finally, I'll look at this. I have my y component and my x component of the last force. Of course, this x component is in the line of action of A, so we don't need it. We only need this y component, which is going to be plus 50 times the y component is cosine 30 times the distance, and this distance is 3 plus 3 plus 3 is 9. So I have these components. I think I did this, did I do this backwards? Yes, my this is not counterclockwise positive, this is clockwise positive. That's okay, I didn't need to fix my signs, I can just say, oops, I accidentally did them all clockwise instead of counterclockwise. So I did them all clockwise, and did I do them all clockwise? No, that one's a positive, that one's a negative. Oh no, I was right the first time. Okay, scratch that, never mind. Okay, counterclockwise positive. If I do this, if I add these all together, punch this into my calculator, I get the moment about A is 270 pound-feet. 270 pound-feet. So that's the moment acting on A for this bar. So now what I can do, since I have this moment, is I can set that equal to my resultant force. And I can say 270, right? Well, let me say it this way. I can say my moment equals F times D. So 270 equals the y component of this force that is in the intersecting with the line of action of the member is 123.3 times the distance away, times that perpendicular distance away. So if I divide this out, I get the distance from A of where this force is actually intersecting, where this resultant force is intersecting with the beam. I plug that into my calculator and I get a D of 2.19 feet. So this is 2.19 feet away from point A. So we often say from point A. So our resultant force is acting about right here, right? This would be where our resultant force is acting. And that's it. That's all we need to do. So sometimes you may need to find the resultant moment or use that resultant moment to find the distance of where this equivalent force is interacting.